In this video cast, we're going to take a look at some calculations to determine the entropy of a particular process or reaction. And if you watched the video cast before, you found out that delta S, which stands for entropy, can be calculated by taking the summation of the standard enthalpies found in the back of the textbook in Appendix C for the products, and subtracting from that the summation of the standard enthalpies for the reactants. And remember that the little circle that we put up here means standard conditions, which means 1 atmosphere, usually 1 mole of the substance. And since entropy is given in joules per Kelvin mole, it stands for the amount per Kelvin unit. And we're usually given that the standard conditions for enthalpy are as well 298 Kelvin. And that's what we usually assume that we're at unless we're told otherwise. In this particular process, we're on page number 13 now, where your sample problems are located. And if you don't have these in front of you, I would suggest you take them out, and then you can follow along with the problems. This one tells us that calculate the delta S for the synthesis of ammonia from nitrogen and hydrogen gas at 298 Kelvin. To find this entropy of the system and to find out whether we are becoming more organized or less organized, we could take delta S and take the products, which are NH3, there's 2 of those, and find the delta S for that from the back of the book. Subtract from that the N2 delta S plus the H2, change in S for that, and we'll have to multiply that one by 3, of course, because there's 3 of those. And if we look these up in the back of the textbook in Appendix C, we find out that the standard enthalpy for NH3 is 192.5 joules per mole Kelvin, and there are 2 of those, so we know to multiply that by 2 because there's a 2 in front of those in the reaction. And we subtract from that nitrogen, which is 191.5 joules per mole Kelvin. And there's 1 of those, so we have to multiply that by 1. And add to that the S for hydrogen, and that's 130.6 joules per mole Kelvin. And there are 3 of those, so we'll have to multiply that by 3. And once we've done that, we can put that into the calculator, multiply these, subtract this group right here, and you end up with negative 198.3 joule per Kelvin, which, since it's negative, it's in agreement with our qualitative prediction that we're decreasing the number of molecules of gas during the reaction. Notice we're going from 4 moles of gas on this side to 2 moles of gas on this side. So we would assume that it is becoming more organized or less disorganized, I guess. And that's why we get this negative number right here. Well, if you flip the page to page number 14, at the top of the page, it has a U-try problem where it says, using the standard enthalpies in Appendix C, calculate the standard entropy change for delta S for the reaction of aluminum oxide and hydrogen and aluminum and H2O. Now, if you understand this concept, you can just fast forward through this part, but I'm just going to do the work on here. So if you want to try it yourself, you're more than welcome to pause right now and look up the entropies in the back of the book, and then see if you can determine it as well. So pause, give it a try, or skip ahead. So the S for this reaction, if I take the products, which are aluminum, Aluminum has a value of 28.3 for a standard entropy in the back of the book. We multiply that times 2. and then we add, this is aluminum right here, we add gaseous water. Notice it's a G there for gaseous water. That's, I believe, is it 188.8? I might have to look that one up quick. I'm not sure whether I looked up gaseous water or liquid water. And if I look underneath the hydrogen oxygens in the back of the book, yep, gaseous water is 188.83. And I need to multiply that one by 3 because there are 3 waters in the product. So that's our products, and subtract from that our reactants. The reactants, aluminum oxide, is 51. And the hydrogen gas is 130.6, and I need to multiply that one times 3 as well. And let's see if I plunk that into my calculator. Those are the numbers that you should have found in the back of the book. I should end up with 180.4 joules per Kelvin as my units on that. And if I look, I'm going from, these are gases over here, 4 moles of gas to 3 moles of gas. So I'd assume that I'm oops, I think this is incorrect. This should be a solid right here. Solid right here. So I'm going from 3 moles of gas to 3 moles of gas. So actually I'm becoming a little bit more disorganized, and I'm adding some entropy to the system. So 180.4 or so joules per Kelvin is what you should have ended up with for that one. Now if you skipped ahead, rejoin with us right now at 19.5, where we're going to talk about the criteria for spontaneity in terms of energy and free energy. So spontaneity, remember, means if a reaction is spontaneous or not. That means it's just going to happen by itself. It'll occur without some outside intervention. In other words, it's going to happen naturally. In terms of entropy, things generally tend towards disorganization. And so generally, we would say that things that have a positive delta S are spontaneous. Generally, we'd say that. Now, that's not always true, but that's what we generally say, is that things tend towards disorder. Now, free energy, if you watched the screencast before this, you were introduced to a letter called delta G, which is called free energy, and that tells us whether there will be a reaction or not. And if you remember those, a negative free energy means that something is spontaneous in the forward direction. A positive free energy means that it is non-spontaneous. And of course, if it's 0, that means we're at equilibrium. Okay? So in terms of positives and negatives, that's what it means. The free energy is the one that really tells us whether something's spontaneous or not. And if we can calculate the free energy, we can find out if there will be a reaction or not. And that's our next sample problem. Calculate the standard free entropy and energy change for the reaction at 298. And to do this, we can use the standard free energies of formation that are given to us in Appendix C. And those are symbolized by G with a small f with a little circle. And remember, the little circle means 298 Kelvin. And we're assuming we're at standard conditions, so we're at 1 atmosphere of pressure, if it's a gas or a liquid or solid. And F means that it's this free energy of formation, means that the substance is formed from its elements at standard conditions. And just like delta H of formation was at that standard conditions, delta G at standard conditions also has a value of 0 for any element in its standard state. Well, we're going to do this reaction. P4 plus a C6Cl2 goes to 4PlC3. And to find the free energy for any particular reaction, we can say that delta G at standard conditions for a reaction is equal to the summation of the standard free energy of formations for the products summed together minus the summation of the standard free energy of formation for the reactants. Notice we're at standard conditions. That's what this little circle means. And the little f down here means that they're the standards of formation, free energies of formation that we can look up in the back of the book. Well, if we look these up in Appendix C, we can do the product. 4PCl3, and we find out that that has a value of, there's 4 of them, so I'll put a 4 down, negative 269.6. Notice this is measured in kilojoules per mole. This is our products, and we subtract from that our reactants. We have 2 reactants here now. We have P4. If you look that one up in the back of the book, P4 is an element in its, let's see, P4 is an element, and it's not in its standard conditions because it's gaseous, if you'll notice here. And that has a value of, let's see, we have 1 of those, a value of 24.4 kilojoules per mole. And then we have to add to that the standard free energy formation for Cl2 gas. Chlorine, in its standard conditions at its standard states, has a standard free energy of formation of 0. So we add 0 to that. It's the summation of those. And if we do products minus reactants added together, we should end up with a standard free energy of formation of negative 1,102.8 kilojoules. Notice the standard free energy of formation is negative. What does that tell us about a reaction? Well, it tells us that it is spontaneous in the forward direction. Now, it doesn't tell us necessarily the speed, but it tells us that it will spontaneously by itself move from left to right if left alone. Bottom question says, what is the delta G for the reverse of this reaction? Well, if you run the reverse of this reaction, you write it as 4PCl3 gas goes to P4 gas plus 6Cl2 gas. And you'd simply take these calculations that we did up here, and we'd flip them around, and we'd do these guys minus these guys. Well, if we did that, we'd end up with the same number that we had up here, except instead of negative 102.8 kilojoules, now we'd end up with positive 1102.8 kilojoules. What does that tell us about the reverse of the reaction? Well, it tells us it's non-spontaneous in reverse. Non-spontaneous in reverse. That reaction won't happen by itself. Has to be some kind of outside intervention. If you flip over to the next page, we have a question at the top that says, without using data from Appendix C, predict whether or not the Gibbs free energy for this reaction is more negative or less negative than delta H. Well, now it asks us not to use Appendix C, and then down here it says use data from Appendix C to see if our prediction is correct. So let's see if we can predict whether it's going to work or not, and whether the Gibbs free energy is more negative or less negative than the delta H. Now it tells us the delta H here is negative 2220 kilojoules. If you remember from the screencast, delta G can also be calculated by using this equation. H minus T delta S. Now H, remember, is the enthalpy, and so that would be a large negative number, negative 2220. T is going to be our temperature, and we know that it's always going to be positive unless we're going to be at absolute zero, because it's always at in Kelvin, and so let's just assume it's standard temperature, and let's 298, so that's going to be a positive number for sure. And our delta S, the question is that going to be a positive number, or is it going to be a negative number? And so we need to qualitatively predict what is going to happen from the left side of the reaction to the right side of a reaction. If you remember back earlier in this chapter, we took a look at that just from the standpoint of, is there more or less organization going from one side to the other? On this side of the reaction, we have 6 moles of gas, 6 moles of gaseous reactants. On the other side, notice we form some liquid over here, so we end up with only 3 moles of gaseous products. Well, when we go from 6 moles to 3 moles of gaseous products, we should assume there should be some more organization going on. And so it's more organized, and therefore we'd assume that the entropy change would be negative. It would be negative. Well, if this turns out to be negative, Now this entire term right here turns out to be H minus a minus TS. A minus is actually a positive value, right? So we're taking H and we're going to add something right here, some amount. We don't know how much, but we know it's going to be something. And so what we would predict is we'd say delta, the G right here, that is equal to our delta H, which is a large negative number, should increase in value as temperature gets bigger. As T gets larger, this amount right here should get larger, and therefore this will become less negative, and delta G should increase in value. Let's see if that actually happens now. It wants us to calculate the standard free energy of reaction at 298, and let's see what we come up with for a value. I'm just going to take the numbers from the back of the textbook here really quick. Carbon dioxide is 3 times negative 394.4. Let's see, water is 4 times negative 237. That's kind of approximate. That's our products minus the reactants. Our reactants here are 1 mole of C3H8, which is negative 23.5 or so. And of course we have oxygen there as well, and oxygen has a value of 0. So products minus reactants, we end up with a value of delta G of negative 2108. Well, what happened to our delta G? Our delta G is negative 2108. We started with a delta H of 2220, and we were supposed to predict whether the Gibbs free energy of this reaction is more negative or less negative than delta H. We predicted that it would increase in value and that it would be more positive. Well, as a matter of fact, it did. It did get a little bit larger. Notice we started at 2220. Now we're at 2108. Did it increase a lot? Well, not a lot, but it did increase, and our prediction was correct. Lastly, we're going to do some problems in section 19.6 involving free energy and temperature. And we're going to look a little bit closer at this equation, G equals H minus TS. And we're going to look at them for the Haber process right here, where nitrogen and hydrogen combine. Notice they're both gases, so there's 4 moles of gas on this side, and they make ammonia, and there's 2 moles of gas on this side. And first of all, we're told that we are to assume that delta H and delta S do not change with temperature, and predict the direction in which delta G of this reaction changes with increasing temperature. What happens with increasing temperature? Well, if we're going from 4 moles to 2 moles, we can predict what's happening to delta S. If we're going from 4 to 2, we would assume that things would be becoming more arranged or more organized. And so we'd assume that delta S is negative, or there's more order or more arrangement happening to it. If S is going to be negative, then this term, negative TS, should turn out to be positive. And so H plus a positive number should give us an idea for what happens with increasing temperature. We should assume that G would become more positive as temperature increases. In letter B, they want us to calculate the value of delta G at 25 and at 500 degrees Celsius and find out if that's really true. And so I've just got some numbers here really quick. And I probably won't do all the calculations for them, but we'll take a look at each one, just plunking it into this equation, G equals H minus TS. And well, we used that to make the prediction, but now we're going to use our delta G, and we'll calculate them using our Gibbs free energies of formation. So we'll do the products summed together minus the summation of the delta G formation of reactants. And if we do those for 2 different temperatures, we calculated earlier that delta H for, well, I think we found these earlier, that delta H for this reaction is negative 92.4 kilojoules, and delta S for this reaction was negative 198.4, and that's joules per Kelvin. So let's take these two values and let's put it into this equation right here, because then we can see how it varies with temperature. We won't be using this one right now, but we'll take a look at how this changes, first of all, when it's 25 Celsius, and then when it's 500 Celsius. If we put these two values in here, we can find that at 25 degrees C, let me zoom out just a little bit here so you get a little bit better view of it. G is going to equal negative 92.4 minus 25 degrees Celsius is 298 Kelvin, times our delta S, which is negative 198.4. Notice this is in joules per Kelvin, and this is in kilojoules. Okay, so what I'm going to do is I'm just going to convert this to kilojoules per Kelvin by moving the decimal point. This is 0.1984 kilojoules per Kelvin. Okay, and when I do that at 25 degrees Celsius, I end up with negative 33.3 kilojoules. Now at 500 degrees Celsius, notice, let's see, we've got still 92.4, except this is now not 298, but 773 Kelvin. And assuming that this doesn't change, remember this is given in joules per Kelvin right here. I'll convert it to kilojoules. That's 0.1984 kilojoules per Kelvin. We'd end up with 61 kilojoules. So was our prediction correct? Would G become more positive as temperature increased? As temperature increased, would it become more positive? We said that delta S was negative, and so this term would be positive. It would increase. As a matter of fact, it went from negative 33 to positive 61. So it went from spontaneous to non-spontaneous, just as we moved up in temperature. If you turn over to page 16, you can see at the top of the page, I have a couple more sample problems. It says, using standard enthalpies of formation and standard entropies in Appendix C, calculate delta H and delta S for the following reaction. So it wants us to find delta H, and it wants us to find delta S. And then using these values, it wants us to estimate delta G at 400 K. So it's assuming that they're going to stay the same, even though we're doing these at 298. Just to save a little bit of time, if you want to go to the back of the book and find the summation of the products minus reactants for each of these and determine them, you're more than welcome to. It turns out that delta H is negative 196.6 kilojoules, and delta S is negative 198.6 joules per Kelvin. If we take these two values and put them into the G equals H minus TS equation, and we're assuming that these values stay the same, even though we were at 298K and we're at 400K here, we can put this into this equation, and we can say that H is negative 196.6 kilojoules minus T, which is 400 Kelvin now, and S, which, watch out now, because this is in joules per Kelvin and this is in kilojoules, so we need them in both the same units. So I'm going to write it as negative 0.1896 kilojoules per Kelvin. Okay, notice how that changes it now. The negative stays the same, but this is kilojoules now. And if I do that math, I end up with G being negative 120.8 kilojoules. And if we take and calculate delta G using products minus reactants, we'd end up with something fairly close, or at least nearly the same as what we calculated right here.